The max patch that we're going to build together analyzes for pitch and then sorts by pitch. The super collider version analyzes by spectral centroid and then sorts by spectral centroid. But it's the same thing. After we do it together, you'll be able to adapt them appropriately. And we're actually going to build the max one together, and then I'm going to hop over to super collider and look at that one, because organizing by pitch will give us a organizing by spectral centroid in super collider code will give us some questionable results to reflect on. Let's put it that way, and think critically about the type of analysis that we're doing. What I have here is a buffer. It's filled with this acoustic bass melody. Also, we could put in the trombone tones. And what I'm going to do is I'm actually going to use this little guy here, which is a bit of an algorithm, as you can see. But what it's going to do is it's going to give me a list of slice points that are going to be 200 milliseconds apart. And it'll just do it for the whole buffer, however long the buffer is. And it'll return to us a list of all of the sample positions. Because remember, with our FluCoMa slicers, it returns to us sample positions, as in audio samples, 44,100 of them per second, about where these slice points are. And so this will give me sample positions of slice points that are all 200 milliseconds apart. So if I just take a look at what that does, I can see, cool, here's a bunch of sample positions that will be 200 milliseconds apart for my buffer called sound, which currently is holding this bass guitar melody. But of course, one could do this with a slicer as well. We're going to take these slice positions and we're going to analyze each one of them for our audio analysis, in this case, pitch. We're going to start from this slice position, 0 samples, and analyze to this position, 8,820 samples. That'll be our first slice. And then our next slice will be starting at this slice point and analyzing to this slice point. Our third slice will be starting at this slice point and analyzing to this slice point. And so we're going to be able to tell the FluCoMa analysis objects that here's where I want you to start, here's where I want you to end, and then give me the audio analysis for that part of the buffer and that part of the buffer only. The way that we're going to do that sort of strategically in Max is we're going to use this object ZL stream, which will give me all of the adjacent values in the list that it receives as pairs of 2. And in super collider, you'll see do adjacent pairs as the method for doing this, which is essentially the same thing. And if we just print that out and see what it looks like, it'll be very clear that what we're getting is first 0 to 8820, then 8820 to 17640, then 17640 to 26460, etc. So we're getting those adjacent pairs, A and B, then B and C, then C and D, etc. And there's one thing that I need to do before we actually do that, which is I'm going to trigger list ZL clear. So first, I will clear my ZL stream so it forgets about anything it has remembered or knows about, and instead we'll just start fresh, and then I'll send my list of slice points in here to do the analysis, or to eventually do the analysis. Okay. So now we'll have those values, our start position and stop position for each of our slices. In order to do the analysis, we're going to use this object fluid.buff, because we're going to do the analysis on a buffer pitch. Fluid.buff pitch. We're going to give it a source, which will be the buffer we want it to analyze. In this case, that's going to be the source called sound. And then we're also going to give it an attribute at features. And this is going to be a buffer where it is going to write the audio analysis into. So another word for analysis is the audio features that it is going to discover or analyze for. And so we're going to tell it where these features should be written into. And as with FluCoMa, as we've seen, we use buffers to pass data between different objects and to hold data. And so here we're using a buffer to write these analyses into. I'll call it pitch buff. That'll be where we will write the pitch information. And then I'm also going to add one more thing here that's going to be at numchans. So the number of channels that this object should analyze for, I'm going to say at numchans1. And in this case, both of my sound files here are mono, but if you were to pass in here a stereo file, Fluid Buff Pitch will analyze a stereo file. It'll analyze both channels separately, and then it will give you back double the amount of data for the left channel and data for the right channel. In this case, to simplify the patch we're making here and the workflow, I'm going to say at numchans1. What it will do is it will actually only analyze the left channel. So it's going to ignore the other channel. Since I said there's a buffer called pitch buff, I better make one. I'll put it right there. And then the last thing I need to tell Fluid Buff Pitch is where in the buffer to actually analyze. There are two attributes that we use to do that. The first one is start frame. And that is going to be the frame or sample position to start the analysis at. I'm going to pass that in by putting a $1 here, because if I peel off the first element in this list of two values, that's going to be the sample that I want to start at. The next argument I'll give it is num frames, which is the number of frames it should analyze for from start frame, right? And right now we actually don't have that information, because what we have is the start and end frame of all of these slices. And I actually want the start and number of frames of all these slices. I actually know that these all will be 200 milliseconds long, so I could just do some math and maybe pass that value in. But a more robust way of doing it would be to do the math by taking the second value minus the first value, and that'll give me the number of frames in between. So the way I'll do that is I'll use a minus object. But rather than just doing minus, which would do the first one minus the second one, I can do a bang minus, and that will do the inverse, the second one minus the first one. And then I'll get the difference between the two. And both of those will go into my Fluid Buff Pitch. In order for Fluid Buff Pitch to actually do the analysis, after I've specified where it should start and how many it should do, it will receive a bang. And so I can do that by using a trigger bang list to first send the lister along, do the math to figure out where to start, how much to do, and then send a bang out there to actually execute the process. In this case, because we're analyzing a buffer that is holding sound, these frames is synonymous with sample, the sample position in the buffer, as in 44,100 of them per second. That's what frame is referring to here. The reason why we use the term frame is because later, as you'll see, we're going to be analyzing buffers again, but rather than holding audio samples, it's going to be holding audio analyses. And then later it might be holding statistical analyses, which no longer will be even organized according to time. And so frame here is just a more generic term to describe like that dimension of a buffer because we're using buffers to hold all this information. So we have frames in one direction, which often is samples, often holds audio samples, and we have channels in the other direction. So it's a two-dimensional data container. Also, I'll point out that the pitch analysis here, fluid buff pitch, is looking for a monophonic pitch signal. So if you have polyphony in that buffer, it'll get confused and it won't give you the results that you might expect, which can be fine and interesting, but just, to be aware of, that's what it is going to give us. Okay, I'm going to use a fluid.buff to list here to get the values out of pitch buff, and we can just take a look at them. Oops. This is going to sort of work, but yeah. So we got all sorts of values over here. So first of all, what this is doing is because ZL stream is going to output all of these pairs of sample positions, it outputs them rapid fire as fast as it can, but each time it outputs a pair of sample positions, the rest of this data flow will take place before the next pair comes out. And so what we're able to do here is basically as fast as Max can compute it all, get a pair of sample positions, send them out, set the start frame, set the num frames, do the analysis, in this case also get the values out of pitch buff and print them. And then once all that is complete, then ZL stream is allowed to send out the next pair. And so we really are doing these in series, one at a time, using this pipeline here for all of it. What pitch buff actually gives us is two audio analyses. One is the pitch estimation, and the second one is a pitch confidence estimation. And this is going to be a value between 0 and 1 about how confident it is in the pitch estimation that it is giving us. The way that it writes the values into this buffer that we've specified, pitch buff, is it turns pitch buff into a two-channel buffer. The first channel is going to be the pitch analysis. The second, or I should say the 0th channel is going to be the pitch analysis. And the first channel is going to be the pitch confidence value. And then each frame in this buffer is going to be the pitch estimation for each FFT frame that is in the section of the buffer source, the sound buffer that we analyzed. So if our 200 milliseconds, our 8,820 samples contains, if there's a hop size of 512, that would be maybe like, what would that be? 10, maybe 13, 15 different FFT frames. In that 200 milliseconds, if we have 15 FFT frames, we'll end up with a buffer that has 15 frames of analysis here. And so the reason that we organize it this way is because as we're used to looking at buffers, the frames often hold audio samples, go from left to right, and is a time series, right? A time series of audio samples that we would play back to play audio. In this case, this set of frames is also a time series, but rather than audio samples, it's a time series of pitch analyses as they occur in the section of the buffer that we are analyzing. And because we're doing an FFT analysis to get those pitch estimations, the number of frames is the number of FFT frames that we have in the section of the buffer we're analyzing. In our case here, we're actually not going to be interested in the pitch confidence. It's actually a really useful analysis that you can use in all sorts of different ways. It also can be like an estimation of noisiness of the signal, these sort of things. But we're actually, for our purposes, just interested in the pitch analysis. And so the way that we're going to get that is we're going to tell fluid buff pitch that we want it to just give us the one analysis. And we can do that by using this attribute select. And select will take a list of arguments here, and we can select which analyses we want it to give us. And in this case, we just want the pitch analysis. So we type in pitch. And now fluid buff pitch won't return to us a 2-channel buffer with all of those analyses. It will return to us a 1-channel buffer with just the pitch analyses. So a nice way of sort of, narrowing down the data pipeline and not having to do too much data wrangling, that in the analysis here, right there, we can specify what specific analysis we want. And it's the same thing in SuperCloud here. We're specifying select centroid because that is the spectral centroid we're getting out of this analysis. The thing we want to do is we just want to get, we want to collect all of those pitch values, and then we're going to sort them according to each sound slice. However, as we've just noticed, for each sound slice, I have as many pitch analyses as there are FFT frames in my slice. So this is a lot of data. We are not going to try to compare every pitch analysis from a slice to every pitch analysis from another slice. Instead, what we want to do is we want to try to summarize one sound slice using one pitch analysis. So each 200 milliseconds, we just have one frequency value that we just say, that's the analysis, that's the pitch. The way that we're going to do that is we're going to take all of these pitch analyses from a single sound slice, and we're going to find the average pitch analysis from that sound slice. And that average will be the pitch value that we use to represent that sound slice. So we can do that using this object in FluCoMa called fluid buff stats. And this will do a statistical analysis on the values in a buffer. I need to say what the source is. So what buffer should I analyze? Should I do statistical analysis on? That's going to be my buffer called pitch buff. And I also need to specify a buffer where I'm going to write the statistics into. And that'll be with the attribute at stats. So I'll make another buffer called stats buff. And then I can use a bang to tell this what to do. I'm going to put a trigger bang in here. And what a trigger bang will do is it'll turn anything it receives into a bang. And this is going to be a little bit of hygiene to keep our patch nice and tidy, because fluid buff pitch, what it actually outputs when it does its analysis is the name of the buffer that it wrote the analysis into. And I don't really want to be passing that onto buff stats. There's actually a way in FluCoMa to sort of automate some of this data passing that's going on. But in this case, I'd rather take this message and turn it into a bang and just bang fluid buff stats to say, okay, we've done the pitch analysis. We're ready to do the stats analysis. Ready, go. So that's how we'll do it here. Okay. So now what fluid buff stats will give us is it will take whatever buffer we give it. So if we imagine it that we're giving it this buffer, which is actually not the data we're giving it, but if we had fluid buff pitch reporting out pitch analysis and a pitch confidence analysis for every FFT frame in our slice, fluid buff stats would take these 2 time series of audio analyses, and it would, for each time series, return for us these statistical summaries of that time series. So for channel 0, which was our pitch analysis, it would give us the mean, standard deviation, skewness, kurtosis, low, median, and maximum values in that time series. And then for channel 1, which was our pitch confidence analysis, it would give us the same statistics for that time series of audio analyses. And you can see the way we're trying to organize this here is that the time series that was in channel 0, the statistical analyses for that time series stay in channel 0. The audio analysis that was in channel 1, the statistical analysis for that time series stays in channel 1. And we will have as many of these statistical analyses for as many of the channels as we had in our audio analysis buffer. Now, before, I was saying that these are time series because they are, right? This is a time series of pitch analyses. We could have as many pitch analyses as there are FFT frames in our slice that we're analyzing. Here, because we're going to summarize those those analyses, that time series of analyses as these statistics, we end up with buff stats will always have the 7 frames with the 7 statistical analyses. So we no longer have a time series. We now have a statistical summary of that time series. Because we are just going to give fluid buff stats the one audio analysis, just pitch, we're actually going to end up with our fluid buff stats here being our stats buff being just the one channel, channel 0, that'll have our statistical analyses of the pitch time series. And we can see that if we use a fluid dot buff to list at source stats buff, and then a print. Here is my, for each of these sound slices, I have my mean, standard deviation, skewness, kurtosis, minimum, median, and maximum audio pitch value for each of the sound slices. Fluid buff stats will give us those analyses with whatever source we give it. We could put an audio file in here. We could put we're putting in this pitch analysis. We could put in MFCC values. It could be any sort of thing that's in the buffer, and buff stats will give us the statistical summary of it. We've sort of outlined these statistics as 7 useful statistics that someone might use, but the mean is very popular. Also, as we'll see later, the sort of minimum or maximum are popular. The median is used a lot. Just like fluid buff pitch, I can actually give this a @select attribute, and I'm going to ask it to return to me just the mean value, because that's what I'm interested in. So now instead of giving me all of the stats, it's actually going to fill a buffer, my stats buff here, with just the mean, which is going to make that buffer 1 frame and 1 channel. That's a very small buffer, but that's what that buffer will be, and that's what it will have there. And now if I do the fluid buff to list, we'll see that we're going to have the single value for each slice, and it's going to be all of the mean values. The 0 here, I think, means silence, as does this 9. 9 hertz is not a hertz that a bass guitar can play. So now we have all of these mean values of each one of our slices. What I'm going to do now is I'm actually going to use this buff to list. Instead of getting them all out and printing them, I'm actually going to collect each one of these in a object ZL group. And ZL group will let me collect all of the values that are sent to it. And then once I'm done collecting all those values, send them out as a list altogether. So I can check that out here. So what I'm doing in SuperCollider is I'm actually on the server using buff compose to copy my singular mean out of stats buff into another buffer called mean centroids. So here, this is where like I'm grouping together all of the mean centroids. And I'm essentially writing it into the buffer called mean centroids at a specific index. And here I'm using the counter as my index here. So that's where I collect them all in a buffer on the server. And then here I'm taking them from the server back to the language, so I can call .order on them. So that's what that's doing. Okay. Before I do the grouping, I actually also need to tell ZL group that I want to clear it. Good habit when using these ZL objects to just clear them right off the bat. And then when I'm done running through all of my slice points using ZL stream 2, I'm actually going to send a bang to the ZL group, which will tell it, okay, now I'm ready to send out all of the values that have just been collected. So this guy should go down here. This guy should go back here and here. Now, if I run the analysis, we should get just one list that has all of the average pitch values for each sound slice. And the next thing I'm going to do is I'm going to sort them. So in Max, there's a great object called ZL sort, which will sort a list for me. ZL sort can give me the sorted list. It also can give me what's called the ordinal, or the indexes of the list reordered such that they will be in order. And this is actually the thing that I want to use, because I want to know how would I reorder this list of mean pitch values. How would I reorder this to be able to play them back in an order that would give me the, give me them organized according to pitch. So that's what this will actually give me, and we can just print it and see that now I should start with I should start with slice 68 and then play slice 69 and then play slice 67 and then 65, etc. And if I play the slices in this order, then I'll get that reorganization according to the pitch analysis. So then this order, what I'm going to do is I'm going to take this order and give it to ZL lookup. And what ZL lookup will do is it'll let me look up basically any one of these integers here. I'll use a counter to look them up in order. So basically, if I send a 0 in here, it'll give me 68. If I send a 1 in here, it'll give me 69. If I send a 2 in here, it'll give me 67, etc. And that way, by rifling through this counter, it'll let me look up all the different slices in the order that I want to play them back in. So I'm going to take this sorted order, reordered indexes list, give it to ZL lookup, and then this will let us access them in order. So this actually is not going to perfectly work for us, and we'll see why in a moment. But we can try it out. So let me do the analysis. We have our ordered list in here now. Then if I turn on the metro, I'll reset the counter, turn on the metro. And it's pretty close, but it actually has a few things that are wrong with it. The reason why we're getting these things that are slightly out of order. It dips down to a lower frequency there. Is because we're using a bass guitar sound, and the bass guitar is playing very low notes, and our default FFT size of 1024 samples is actually not going to be good enough at capturing those low frequencies to give us an accurate pitch estimation. So what we can do is we can actually tell Fluid Buff Pitch that we want it to use different FFT settings, ones that'll give us a better analysis in that low register for the bass guitar. And then, and then we should be able to get a better pitch analysis here. So I'll give in the attribute here at FFT settings. The first argument is going to be my window size. The default is 1024. I'm going to change it to 4096 samples. The second argument is the hop size. I'm going to change that to 512. So I'm doing an overlap of 8 here, right? I'm starting a new FFT analysis every 512 samples, but every FFT analysis I do is 4096 samples long. So quite a bit of overlap. But remember, once we do all of these analyses, we are then taking the average analysis over that sound slice anyways. So we'll still end up with just the one average pitch for each sound slice. Do the analysis. So here's our new order. And then if I play this back, And if we listen to the trombone, which we've heard, and so I can load in the trombone recording. We have that there. And then find out where the slice points should be for every 200 milliseconds. Looks like we have 285 slices in that case, or 285 slice points. Do the analysis. Longer file, takes a little bit of time to compute. And then reset the counter and listen to this guy. All of those trombone tones organized according to pitch, or all of those grains of trombone tones organized according to pitch. Okay, I'm actually going to hop over to the super collider version for a moment, and we'll listen to the same idea, but using spectral centroid and a drum loop. So I'll just go through these things. We're actually slicing according to amplitude. We're going to slice the drum loop according to the amplitude, so we'll get the individual drum hits, or as time slices. You can see them there. And then we'll do a similar analysis for spectral centroid. We'll get the order out here. Here's our order of drum slices that will organize them according to spectral centroid, just like we did with ZL sort. And if we play them one at a time, so if we think about what we have some kick drum in there, we got some snare in there, we have some cymbal in there. And if we're organizing them according to spectral centroid, we might expect to have all the kick hits first, then the snare hits in the middle there, and then all the cymbal hits at the end as our brightness of our drum surface goes from low to high. When we listen to it, we'll hear some of that happen, and we'll also hear some things that seem out of place, and we're going to reflect for a moment on why we think that is. Even that last one there has some kick drum in it. We're slicing it by the onsets, and some of these moments in time that we're analyzing have some kick and some cymbal in it. And so when we do the analysis, what we end up with is something where we get a slice analyzed for spectral centroid, but that slice might have some cymbal and some kick in it. And so when we take the spectral centroid, we're trying to find the center of the spectrum, a sort of weighted average of all the FFT magnitudes. And we're going to end up with something kind of in the middle. As opposed to if we had something that was just cymbal, I know we have this here, but this is like some DC offset noise. We have just cymbal, we're going to have a much higher spectral centroid, or just kick, we're going to have a much lower spectral centroid. And so even just looking at what we have in one FFT frame. We could have a spectral centroid that is going to be confusing once we try to sort because we have multiple sounds happening in one slice. Also, as we take the mean value, if we have a slice where we have some kick in the beginning and some symbol at the end, right? So this might be our spectral centroid curve. If we take the mean value across a slice, even this is going to give us something that is going to be a poor representation of our sound slice as a spectral centroid estimation, because the average is going to be somewhere in the middle between these higher values and these lower values. And so it's not going to be the best way to summarize the slice using spectral centroid. And actually, arguably, this is not a great spectral centroid. Taking the mean spectral centroid would not be a great way to try to organize these different drum hits, right? So one thing you could do is maybe do the NMF analysis we did yesterday first, and then slice according to amplitude, and then organize according to mean spectral centroid. That would be a much more successful approach. So this combination of, slicing in time, separating in spectrum, and then doing the analysis, this is a common way of trying to get at what it is that, you care about in the sound that you want to be able to analyze, that you want to be able to represent these sound slices as, and then do something creative with them. This, a lot of times the FluCoMa toolkit, people talk about the neural networks and the plotter and the dimensionality reduction and all these sort of data science machine learning tools. And people talk less about these sort of first steps of slicing and spectral decomposition and these things. And, but in order to use those data science tools in ways that can be really creatively powerful, it's important to get comfortable with these other tools as well, to be able to get at the thing in the sound that you care about. The machine learning algorithm won't just figure it out for you. You have to do some thinking about, what do I care about in the sound? How can I get at that? How can I represent that numerically? And then how can I give it to some data science